to Current Affairs for UPSC by ZAKI. Today we are going to discuss about the galaxy-sized observatory for the gravitational waves. So see what are this observatory and what is gravitational wave background and why this topic is significant for the civil services examination, basically UPSC. So as you know, in 2018, UPSC asked question from the LIGO, and in 2020, UPSC asked question from the IPTA. So we also discuss on this all topic and about ELISA and what is LISA pathfinder, and after that we also discuss about the observatory for the gravitational. So first observatory, LIGO, which is situated on the ground, and second observatory, scientists move far beyond the ground and in the solar system, and that is called LISA. And finally, scientists move more and more and far beyond, not in our solar system, it is a galaxy-sized observatory. So what is this galaxy-sized observatory? So stay with me who know about what is this galaxy-sized observatory. So before we going forward, you don't forget to subscribe my channel and tell your friend about our initiations for the basically ISPT 2021 special video. So let's move forward, and that is galaxy-sized observatory for the gravitational waves. So scientists recently basically research basically a new finding which appeared recently in the General Astrophysical Journal later. Hails from the US and Canadian project called North American Nanohertz Observatory Gravitational Waves. In short, we can call it NANOGrav. So it is NANOGrav. North American Nanohertz Observatory and Gravitational Waves. So in short, it's called NANOGrav. So we move forward and see what is gravitational wave diagram. Gravitational wave diagram. So see basically NANOGrav team are working for gravitational waves around 30 years, and researchers have poured over the light streaming from the dozens of pulsars spread through the Milky Wave's galaxy to try detect the gravitational waves background. So how they can able to detect, or what is the mechanism for the detections of the gravitational waves basically applied by the NANOGrav researcher of NANOGrav team. So we move forward and see here. Basically, what Einstein tell about the theory of relativity and basically relation to the space and time. So if we see here, first from here is it is our sun. So if we see the gravity is not only the pulling force, you can see it in the relevance of the time and space. So see here, and here is up. So this type of coordination generate a ripple in the gravitational force. So that's all, and basically this is some see here, and basically what the scientists use, this is pulsar. Pulsar is a neutron star and moving very fast and creating radio burst and gamma ray burst, and it is basically reached Earth in the constant times. So if you see in a scale, it is a some steady pattern like this, or you see like this. So all person seems some steady pattern. So if you imagine some black hole here, two black hole merge, then these two black hole give a gravitational waves. Like you put a stone in a pond and that's ripple, and after that ripple present in this area or in this area, the time between these two steady pulses of the pulsar is affected by the gravitational, and finally the scientists able to detect the difference between the time. So that's that about this one. But we also see animation about the gravitational waves background, and after that you can easily understand what is the gravitational waves and what are the pulsar. Is very useful to detect the gravitational waves. So we move forward and see what scientists call the steady flux of the gravitational radiation that, according to the theory, passes over the Earth on a constant basis. So the team has not yet pinpointed the target, but it's getting closer than ever before. Say Joseph Simon, basically is the lead astrophysicist at the Colorado Boulder University, and lead author of the new paper. So, what new paper published in Journal Journal of Astrophysics. So, we move forward and see the LIGO. Basically, as we earlier discussed with you, we discussed all about LIGO, EDISA, and all that. So, LIGO, basically, the Nobel Prize in Physics in 2017, and basically in 2017, scientists on an experiment called LIGO. LIGO is a short form. Basically, it is called Laser Interferometer Gravitational Waves Observatory. In short, LIGO. Won the Nobel Prize in Physics for the first ever detect the gravitational wave, what Einstein predicted a century before. So these waves were created when two black holes slammed into each other roughly about 130 million light years from the Earth, generating a cosmic shock that has spread to our own solar system. So that's LIGO detected first time the gravitational waves. So a violent and short light burst. So basically, it is a very strong waves. This event is equivalent of a Kimball crash, a violent and short-lived blast. The gravitational wave that Simon and colleagues are looking for, in contrast, the more like the steady hum of the conversation at the crowded cocktail party. So see, what kind of gravitational waves detected by LIGO. Basically, if you see here are it is gravitational waves. It is gravitational. So Earth detect this at this level. It means Earth from Earth you can detect about 1,000 hertz frequency, basically wavelength. And so if we want to detect long wavelength, then Earth is not enough. So if such kind of gravitational wave reach will be made by the huge supermassive black hole collide each other. So see here, this. So if the waves of this type of hue and Earth is so small, then it requires 10 Earth. If the wavelength is 1 lakh hertz. So it means it requires 10. So that's why scientists want to use a device or use a natural device which is nature present provide us. It is called pulsar or neutron star or pulsar. So that's why that this is and it is also it is a steady and conversion. So it is a not such kind of the you detect and go. So that's why scientists want to detect our cosmic wave, our gravitational wave back far beyond our solar system, and it basically it is in our galaxy. So see, and we move forward and see. So we move forward and see detecting that background noise would be a major scientific achievement, opening a new window for the working of the universe. So basically, these waves, for example, could be give scientists a new tool for how supermassive black holes at the center of many galaxies merge over the time. So if we have and can able to made a galaxy size observatory which is uses the pulsar, we can detect a supermassive. One thing is also very significant for the gravitational waves background. So if we, in contrast of that cosmic wave background, then if you join our class or if you are my student, I earlier told about the origin of the universe and origin of the earth. So if we scientists map the cosmic wave background are basically generated after the thousands of lakhs year after the Big Bang theory. But gravitational waves are basically at the time of the Big Bang, at very short time after that Big Bang. So if we able to detect gravitational wave, then we able to go to the far beyond and near there to the Big Bang theory and all. So that's all. So we move forward and see pulsars at galactic lighthouse, or it is called galactic lighthouses. So basically through their work from the basically Simon and their colleagues on NANOGrav confirm uh, comfort are light of the state and with collaboration of international rays find gravitational wave background. So if we see the international pulsar timing, and basically these gravitational waves basically not detect directly by detect by the observing the pulsar. So there is an institution in our Earth. It is called International Pulsar Timing Array, or it is called IPTA. So know about what is International Pulsar Timing Array. Their project to basically Siemens and their colleagues, two others, European and Australian, to make a network called the International Pulsar Timing. So it is an international network, institutional, basically International Pulsar Timing. So see what is International Pulsar. Move forward and see. The International Pulsar Timing Array is a multi-institutional, multi-telescope collaboration comprising the European Timing Pulsar Timing Array (EPTA) and the North American Nanohertz Observatory for the Gravitational Waves, and in short we called it NANOGrav, and the Parker Pulsar Timing Array (PPT). So all these three included in the International Pulsar Timing. So we move forward. The goal of the IPTA is to detect gravitational waves using an array of approximately 30 pulsars. So this program will use about 30 pulsars in our Milky Way galaxy. So say the NANOGrav and the Pulsar. Basically, the NANOGrav team uses telescope on the ground not to look for the gravitational wave, but it is observe the pulsar by the telescope. So these collapse star, basically pulsars, are called lighthouses of the galaxy. So basically, it is blink like lighthouse in Earth. That so the scientists call it lighthouse of the our galaxy, or it is also called galactic lighthouse. So they spin at incredibly fast speed, sending streams of the radiations hurtling towards the Earth, blinking pattern that remain mostly unchanged over the eras and eras. So it is a steady radiations of these pulsars. So it is basically incredibly fast. We see in animation also incredibly fast, even 100 and 200 and 300 rotations in per second. So it is very fast rotating object. So see, the gravitational waves alter the steady pattern of the light. So these steady pattern from the eons and era altered by the gravitational waves. So Simon explained that gravitational waves alter the steady pattern of light coming from the pulsar, tugging or squeezing relatively distances that these rays travel through the space. So scientists, in other words, might to be able to spot the gravitational waves background simply by monitoring the pulsars for correlated changes in the timing of when they arrive. As we earlier told you, see, there are pulsars, pulsars are fast rotating, and they emit radio burst, and that is if gravitational waves from two colliding stars, two supermassive black hole, or two supermassive neutron and supermassive black hole, and etc. Maybe so. Okay. So these gravitational waves distort the timing. This timing after gravitational waves, short distance. So these distortion detected by the scientists on the ground by the telescope, and finally, after observing that, they able to detect the gravitational wave background in future. So that's all about the gravitational waves, and we move forward and see animation of the gravitational waves background. And yeah. So further we see the animation of the we first start from the LIGO. So it is the first merger of two black holes, and detected gravitational waves detected by the LIGO, and they won the Nobel Prize in 2017, and also asked the UPSC question in 2019. So, gravitational. So this is LIGO, and basically this is all spread about 4 kilometers. So it is basically too small. So in 2015, European Space Agency sent another. It is called LISA Pathfinder. Basically, it is a European Space Program. So it is called LISA Pathfinder. Is a spacecraft. So the LISA Pathfinder is the name of the spacecraft, and the total satellite, three satellite with the 5 million kilometer arms are basically ELISA. So ELISA project basically is the European Space Agency project. So that's ELISA as in 2020. So see animation about that ELISA. This is the ELISA devices, and basically it is basically beaming the laser and approximately about these are about 5 million kilometers from each other sector. So see. So it is 5 million. So after that, scientists know that maybe some black hole merger is very large and very very large and very big wavelength beyond our solar system. So we need to make a galaxy size observatory for detection of the gravitational wave background. So that nature provide us various natural objects like pulsars. So see our galaxy, and it is called a pulsar. So see, pulsar is a neutron star and fast rotating neutron star. So see, and it is a high magnetic field, and it is basically radio burst and gamma constant. So see here. So after that, like this is a supermassive black hole collide, and if all many galaxies in our universe have supermassive black hole collision in the so we can if we can able to observe with the galaxy size observatory, we can able to detect these kind of gravitational. So we need a galaxy size. So galaxy size. So see, if here is Earth, and this is all about pulsars situated in the our galaxy. So see, so, okay. So we detect gravitational waves all in our galaxy system. So nature provides all about, basically it is the time, basically it is our time scale of the galaxy system. So imagine a supermassive black hole and a small black hole merging towards this type of. So after the merger, they send very heavy gravitational waves towards our galaxies here, and so these galaxy and these wavelengths come to the waves come to the Earth. So see, if we all these point we have find a pulsar, then we can easily detect these, and the signal come from the universe to our Earth. So after these signals detected in the various places of the Earth, situated around the globe, so these basically it is International Pulsar Timing Area, IPTA, or it is we called in IPTA. So see here, it is situated in the America and Canada. It is situated in the Europe, basically UK, Italy, France, and Netherlands, and it is situated on in South Africa, India, and China, and Australia. So this area is situated in various parts of the globe, and fortunately, our India also. So after the detection, we can find very large merger across the universe and globe, and we can finally find, we can able in future to find the gravitational wave background far beyond the cosmos. So that's all about the galaxy size observatory for the gravitational waves. So that's why it is called galaxy size observatory. Not it is a short, small, or teeny device made by the human. It is made by the nature. So we move forward. Our next section. Next section is question for the which of the following celestial body are called lighthouse of the galaxy? Quasars, A, B, supernova, C, pulsars, D, supermassive white hole. Please write your answer in the comment box, and don't forget to subscribe my channel. So for this kind of video, basically this video is very significant for the UPSC point of view. In 2019, as you know, question asked from the LIGO. In 2020, question asked from the ELISA, and maybe in 2021, maybe question asked from the NANOGrav. So it is very significant chapter, basically the UPSC point of view. So don't forget to subscribe my channel, tell your friend, and after you after the completion of the 500 subscriber for my channel, then we start a mapping class, and mapping class is free for 500 subscriber. For our subscriber, it is absolutely free. So share this video, like and comment. If you want to more video on this type, you can comment, and you can contact directly. So we move forward, and our next section is answer of the previous question. So see, answer of the previous question. Consider the following statements. The India's official forecast rely on the output of dynamical model. It is wrong. It is not dynamical model, it is a statical model, not dynamical model. So this is wrong. In dynamical model, the climate on the particular day is simulated on supercomputer and meteorologists observe the changing daily output. It is right. So see, which of the above statement is correct? A only, A one only, it is wrong. B two only, it is right. C both 1 and 2, it is also wrong, and neither 1 nor 2, it is also wrong. So answer is D. So this is also wrong, this is also wrong. So answer is, that's all about the gravitational. So tell your friend and colleagues about our initiations. It is our 32 video, and after 45 video we also provide you a short video on the concept clarification. So if you want to join our concept clarification, you must subscribe our channel and tell your friend and colleagues and share as much as you can, because it is your channel. So thanks for watching this video. We will meet in the next video. Thanks a lot.